Okay, class, we're going to do another bundle here of videos. We're going to start with the laws of sines and cosines. Right, click on here so it moves. There we go. Okay, oblique triangles. Anything but a right triangle can't use Pythagorean theorem. So you can only use Pythagorean theorem with a right triangle. There is an opposite side, but there's no hypotenuse in most triangles. There isn't an adjacent side either. There is only opposite sides of the angles. So data required for solving oblique triangles. One side, two angles are known as side angle angle or angle side angle. Uh, Two sides and one angle not included between the two sides are known as side-side angle. This case may lead to 0, 1, or 2 triangles, and this is called the ambiguous case. It doesn't quite give you a good answer. Two sides and the angle included between the two sides are known as side angle side. And three sides, side, side, side. Angle, angle, angle does not give a unique solution. Okay. So these are some congruence properties you guys should be familiar with. The law of cosines in any triangle ABC with sides little a, little b, little c, the following holds. A squared plus b squared plus c squared minus 2 times b times c times cosine of angle A, and so on. So it can be written any way, whatever way is convenient for you, depending upon what you're looking for. Just understand that you're taking whatever is on the left side, so whatever side you're really got the focus on is the angle that you'll use on the other part. That's how I think of it. It's if this is I if this is A, then this angle will be A. It also means that this chunk will be from here and from here, right? So it'll be those. So the square of the side in any triangle is equal to the sum of the squares of the other two sides minus twice the product of those two sides and the cosine of the angle included between them. The angle always matches the side on the left of the equation. Only two sides appear on the right of the equation. And if the angle is 90, it actually is the Pythagorean theorem. This piece here, this one directly here, becomes a Pythagorean theorem if C is 90, right? So this could prove, if you wanted to, the Pythagorean theorem. More importantly, it proves the converse of the Pythagorean theorem. Used for side angle side and side side side. These are common uses for it. Here it is. I have some gamma. That's my angle. I have side A, B, C. I did put a height down. I did drop an altitude down to do the proof. So left triangle is cosine of gamma is equal to the adjacent over the hypotenuse. And the adjacent is equal to A times cosine of gamma, right? Because the adjacent isn't all of B, it's only a part of it. The left-hand triangle would be A squared, that's capital A squared, that's my one side, plus H squared, or is equal to H squared plus A cosine gamma squared. So that's great. So we're clear. This isn't like I just solved for the word adjacent, right? That's how I got this over here. I solved for the word adjacent. Um, so this is what I have. Um, I clean up because I'm looking for my height. I want to set it equal to my height. Why do I want to set it equal to my height? Well, because my height is going to relate to the other triangle because it's the same for both. So the right-hand triangle, that would be c squared is equal to my height squared plus b minus that a cosine of gamma squared. So kind of putting pieces together, I took this, put it in here, right? That's all I did, nothing crazy. Going to clean this up a bit because that's kind of ugly. So that much looks much better. Uh, all cleaned up. Now let's combine terms, right? That's the goal here, combine terms. What do we have? Well, I have a squared plus, or c squared is equal to a squared plus b squared minus 2abc because this piece here and this piece here go to 0, right? Law of sines. Law of sines is nice. We like law of sines. This is A over sine of alpha, B over is equal to B over sine of beta is equal to C over sine of gamma, uh, or 2 times the radius. Yep, it is. Why? Because they're nice circles. These are ratios. The 3 ratios are the lengths of the side to the sine of the angle opposite it are all equal to 2r. R is the radius of the circle that circumscribes the triangle, whatever that triangle may be. And this is useful for angle, side, angle, angle, and side, angle. And there you have the shapes. Um, and I should connect like that. The side, so this side right here, has the same relationship with this side, right, as these others do. So as this one does and this one does. They have the same ratio. Uh, you guys know if you look at gamma or alpha, because alpha is the largest angle here, that's the largest angle, it must be opposite the largest side. Gamma is a smaller one, so it's opposite a smaller side. And same thing with beta. Now, do you know whether beta is bigger or smaller? You don't, but these are opposite. And that is always the case, that these will be opposite a corresponding side that is the same relation. So these ratios will always be consistent. Okay. Um, all 3 ratios of the sine of an angle to the length of the opposite side it are equal. Uh, so in Euclidean space, remember that 3 angles must in a triangle must add up to 180 degrees. And again, that is true in Euclidean space, and it's not true elsewhere. In fact, it's only true on the board you write on and the papers you draw on. But actually, when you work in the regular world, that is never the case. So here's the relationship. If I have A over sine of alpha, and I say it's equal to 2r, so how do I prove that? Well, I look at these segments, OP and OQ. So those are those 2 segments that I just made. And I can go down and there's my midpoint. And the midpoint of PQ is M. So POQ, right? POQ, or angle O going down, has a measure of 2 alpha. And MOP bisects POQ, so it has a measure of alpha. Okay. Right, so MOP, which is this one, right? I want to be clear we're talking this one. So this angle here is alpha, okay? PM has a length of A halves, half of A, right? We knew that, okay? OP has a length of R, right? So just in that little triangle, I have some information. So the triangle MOP is a right triangle by design, right? This is the right angle right here. I don't want to touch the screen. That's the right angle. So sine of alpha is equal to, remember that this is alpha. Let me see. That there is alpha, right? So sine of that angle is the opposite side over the hypotenuse. So this is the opposite side. That's the hypotenuse. Cleaning that up, we see that it's equal to A over 2R, uh, which we can then solve for 2R, and we have A over sine of alpha. And you can do this with the other side, and so on down the list. You can do this throughout the whole thing. So ask a mathematician to say something and not prove it, not easy. I feel like proving stuff means it's stronger. Proofs are true whether we are here or not. They are always true. So here's some of the homework. So these are introductory exercises about congruence theorems. What does it mean for two triangles to be congruent? You're going to write some sentences, maybe something along the lines that for congruence of triangles means that two triangles um, are said to be congruent if all three corresponding sides are equal and all three corresponding angles are equal. So they can be rotated, flipped, and or slid to look identical. Something along that lines. Use your own language. Part B, you get to assume that side, 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 and side angle are all valid congruence theorems. Discuss and draw a picture illustrating the meaning of each of these. So what is this going to look like? I'm not going to do it for every one of these, but let's just look at, let's do something like this. So first, two triangles, and I want them to be congruent. Pretend these look alike. We'll label this A, B, C. So we'll label this one D, E, F, right? That's not an F. Where's the eraser? Erase. There we go. That's an F. All right. And what does it mean? So, well, this means that uh, AB is equal to DE and BC is equal to EF and AC is uh, equal to DF. Um, and so this is the picture and a little statement. The triangle ABC is congruent with triangle DEF. I would say something like all uh, corresponding sides are equal and by side, these triangles, you should probably write that out, are said to be congruent. So there I have a picture stating it, and then in words to be very clear. You would do that for side, angle, angle. So we're discussing the meaning and we're drawing a picture. And then C says, is angle, side a valid congruence? If so, briefly show. So the question is it? And repeat the process with angle, and side, angle. Okay, so let's go back. Is angle, side? Ooh, that's a good question. Is angle, side? Let's see. Maybe do this in a different color too. Let's use that color. Okay. All right. So um, let's maybe instead of drawing a new picture, let's maybe assign some stuff. Might need more alpha, B, gamma. And we would have angle, side. Okay. So then this would be alpha, B, and then this would be gamma. Okay. And then we have this side and this side. So same letters. The question is it congruent? Well, so we also know this. So the other piece we know out of that, so I would maybe redraw the picture, right? But I'm not going to because of space. I know that gamma in the first one is 180 minus alpha or theta plus b. And I know in the other one, it is exactly the same thing, right? It is 180 minus theta plus phi. Okay. So using the idea that I know that gamma is the same because I know that theta and phi are the same, then let's see, what would I know? I would know since all three angles must equal 180 in Euclidean space. All three angles must be equal. Equal. So this would mean we would have angle A is equal to angle D, which I labeled as theta, and angle B is equal to angle E, which I labeled as phi, and angle C angle F, which I did as gamma. Technically, this is by the third angle theorem. I mean, and I know that BC equals EF. Equals EF. So remember that the goal of this was to show that uh, angle, angle, side, or side, angle, angle, which those are equivalent, show that they're true. Interestingly enough, because we found the other angle, we can say, hence by angle, side, angle, which we had done above, right? Which we had already done above, angle, side, angle, uh, triangle ABC is congruent with triangle DEF. So we might say, therefore, angle, angle, side is also a congruence theorem. You guys will write those out. That's part C. C, right? This is part C. Part D, what was part D? Part D was the ones that, yeah, angle, 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 and side, side, angle. So, probably not enough room to fit that in. Let's see what we can do here. Okay, so if I look at a triangle, so this maybe I do this with angle, angle, angle. Um, I feel right. I feel this one's pretty straightforward. Draw a scaled triangle. So draw one triangle and then scale the other triangle. So I'm going to leave that alone. Let me look at this one. This one is probably a little bit harder. Uh, so if I take triangle and A, B, C, and that's not going to be, just so you know, an angle D, E, F. Okay. Now let's put this one is the same. So this one here and this one here will be the same. And then I need which sides to be the same? I need this side, and this side, this side. Okay, so those sides are the same. So I have side, side, angle, side, side, angle. Okay. Um, we could write that the other way, angle, side, side, angle, side, side. It's equivalent. I'm just not writing it that way because, yeah, no. Okay. Uh, maybe I might say something like, since angle C and angle F are not between the congruent sides. The sides uh, we cannot say whether triangles are congruent. Okay. Um, all we have is this. This is all we have. We have angle C is equal to angle F. We have that AC equals DF, and we have that AB is equal to DE. Uh, so thus side-side angle does not imply congruence. I would not abbreviate as much as I do in your write-up. This is, come on. Okay, this is this piece. The angle, like I said, I really believe that's just a matter of, well, stating it right. Draw a triangle and then draw a bigger version of the same triangle. Pretend these look alike. They would imply that they're not congruent. Every one of the angles would be exactly the same, but the sides would not. So you're going to use a scale multiple to prove that. I feel that one's pretty straightforward. What was the previous one? Okay. Does the value of cosine uniquely determine an angle gamma, satisfying that gamma is between 0 and pi? And why? So, um, so it does. It's unique for all angles, which lie in the range. So yeah, I would consider that. How would you do that? Well, maybe look at some properties that you know. You know that uh, so it's asking about cosine of gamma. So does it? Well, cosine 1 at uh, gamma equal to 0 degrees, right? 0 degrees, 0 at gamma equal to pi halves, right? Our interval only goes up to pi, so 0 to pi. And then at -1, right? This is me knowing what a cosine function looks like. You guys should know what a cosine function looks like. Yeah. So yes, it's going to go from 1 to -1 to 1. So yes, it does. Uniquely, yes, it absolutely does uniquely determine. So maybe say that. What's B? B, if you know the three sides of a triangle, then the law of cosine says, okay, use the law of cosine to show that if we know all three sides of a triangle, say the length of A, B, C, that we can uniquely determine all three angles. How does part A play into this rule? Well, if you know that, maybe make gamma opposite side C, you would have a triangle that looks something like, uh, well, something like this. Let me see. See if I have enough room to big triangle, right? I need a big triangle. This is going to be, I'm just going to write all over this. This is side A, and let's make A opposite alpha. And then this will be B, because this is going to be beta, right? And then this is going to be gamma, gamma C. All right, so then using the law of cosines, I'm going to manipulate. I'm going to move stuff around, and let's see. Uh, we want to solve for uniquely, so we want to solve for uniquely for gamma. It means I'm doing the cosine inverse. So I'm just going to write over here, just because there's empty space. Gamma would be equal to cosine inverse of BC squared minus A squared minus B squared over minus 2AB. Yep, yep. Um, then do that for, right? Do you guys, well, you got to manipulate it. So you manipulate law of cosines to get that. Okay. And then do same for alpha and beta, right? And you'd actually have them written, those angles, in terms of your sides A, B, C, and cosine. And then that's B is, let's see, how does A play a role in the process? So A is useful as cosine. Oh, yeah. So using part A, right? Cosine inverse of a negative number is an angle, or will give an angle uh, between pi halves and pi. Whereas cosine inverse of a positive one, a positive number, that will give an angle between 0 and pi halves, right? So yes, part A is important, and this is how it plays a role. So there's a few pieces there. You guys can put it all together. Construct a large triangle. You draw one. Measure the three side angles. So you get to use a ruler. Um, and then use the law of sines to compute the cosine of each of the angles in the triangle. And then use your figure from part C, measure the angles, and compute the cosine of the angle. Measures. How well does cosine you just computed agree with the cosines from part C? How do you measure angles? Well, you use a what? Protractor. Use a protractor. Measure it. Should it be exact? No. Uh, should it be close? Yes. A lot of it is going to depend on if you do your roundings. If you round early, it's going to hurt you, and you probably won't get close. Uh, but yeah, otherwise, protractor is your friend on this one. I think that was it. Let me get over here. Yep. Again, the assignments. All right. That's it for this one, and I'll start on another one.